So in our new unit, the first thing we're starting with is the chain rule, because often what happens in math is you have one function embedded inside of another function. Composition of functions. We usually write it like this, f of g of x. There's sort of two notations. I like this first notation, f of g of x, with a little circle there in between. I think that's a little confusing. It even spells the word fog, so it's like foggy, confusing, unclear. But you can see both of those notations. So here, I have a 3x plus 2 inside of something being cubed. So the question is, what's the derivative? Right now, we don't know a shortcut to do this. So the only thing we could do is multiply it out. Using Pascal's triangle, or whatever way you'd like to. Here I'm using the numbers from Pascal's triangle. And if I simplified that, I would get this. In this form, it's just a simple power rule derivative. No problem. But if I had the same question and instead of an exponent of 3, I had an exponent of 7, I might get a little frustrated. And I might say, I wish there was a shortcut. And what we've been discovering in calculus is most of the things, if you wish there's a shortcut, there probably is. So we're going to find the shortcut for this, and we're going to find the shortcut by looking at a pattern. If I multiplied this out, and I got this as an answer, and then I simplified it, okay? I could now easily take the derivative. And if I look at that derivative, I could factor it. I could factor out a common factor of 9. And then I notice that the other thing factors to 3x plus 2, 3x plus 2. And I get 9 times 3x plus 2 squared. You're lucky I was getting Okay, so first glance here. That's kind of interesting. Doesn't it kind of look like it used the power rule? Because we have the 3x plus 2 and minus 1. But instead of a 3 out in front, we have a 9 out in front. So we're like, huh. It seems like there should be a shortcut here, but why is it a 9 and not a 3 out in front? And so what mathematicians would do in this case, if they were looking for a shortcut, they'd say, well, maybe I look at a few more. And if I look at a few more, maybe I can see more of a pattern. So here are 4 more. And can you imagine actually doing this to the power of 40? And then using like the factor theorem and remainder theorem 38 times with synthetic division to factor it to find out it just works out that way. And then look for a pattern. Does it not look like the power rule is used every single time? And then there's an extra factor that happens to be the derivative of the inside function. And so we're going to develop, I'm going to add one more here. If this is my original function, the chain rule says, do the derivative of the outside function first. So in this case, the power is the outside function. Do you know how to do the power rule? Yes. You would bring the 8 out in front, which would make the number in front a 40. You keep the inside the same, and subtract 1 from the exponent, giving me a 7 there. That would be a simple power rule. So the chain rule says, do the derivative of the outside while keeping the inside function the same. And then when you're done, multiply by the derivative of your inside function. The challenge with the chain rule is recognizing which is your outside function and what is your inside function. Power rule is really easy to see that the x to the 7 plus 2x is inside something to the power of 8. The chain rule is written like this. And I often put in here so what you do is you do the derivative of the outside function, keeping the inside the same, multiplied by the derivative of the inside function. And I think it's easiest to see here. I'm going to just highlight the inside function. Function notation, the second one is easier to understand. So g of x is my outside function. I mean, g of x is the inside function. So my derivative of this whole thing would be the derivative of my outside function, keeping my inside the same, and then I multiply by the derivative of the inside function. Leibniz notation says dy du is the derivative of the outside function, and having the u on the bottom means keeping the inside the same, multiplied by the derivative of the inside function. So the Leibniz notation is a little bit trickier to see it. I find that the second notation helps you see it a little bit better. But Leibniz notation, like, if you did your basic fraction rules, do you see how these du's would like cancel out if they were like numbers? And dy dx equals dy dx? Leibniz's notation is actually really cool because a lot of fraction rules apply to Leibniz notation even though they're not numbers. And even though technically you shouldn't do that when they're not numbers, but it still works out, which is kind of nice. So we're going to look at some examples of how this works. And we're going to start by using the Leibniz notation, which we will never ever use again because it's really messy. But we'll look at formally how you would do that, and then we'll go away from it. In fact, I so much want to go away from it, I'm going to even go away from it right at the beginning. Because this is how you're going to do the chain rule every single time. You're going to recognize what is the outside function, what's inside. In this case, can you see that the 3x plus 6 is inside being the power 5? So my outside function is the power 5. How do I do a power rule? Comes out in front, subtract 1 from the exponent, keep the inside the same. Multiply by, what's the derivative of the inside? 3. That's what you're going to do. That's all the work you're going to show. I feel bad showing you the proper Leibniz notation because you're never going to use it, but this is what it looks like. If you are using Leibniz notation, you have to label your inside function as the u. So here is my inside function. U would equal 3x plus 6. Then I could rewrite this equation as y equals u to the 5. If I have y equals u to the 5, then this part of the chain rule, dy du, is 5u to the 4. You're taking the derivative of derivative of y with respect to u, just a simple power rule. I have an equation that u is equal to 3x plus 6. I could find its derivative. Du dx would just be 3. Then I plug those things into my formula. dy dx would be 5u to the 4 times by 3. Substitute back in. I could simplify the 5 times 3 if I wanted to, not necessary. This is Leibniz notation. However, most of you will just most of you will be able to just say, I do the derivative of the outside function, keep the inside the same, and then multiply by the derivative of the inside. This is almost like Halloween part 2. Okay. So again, I'm going to show you the nice way first, and then go back to Leibniz notation. First of all, if I was doing this one, where do I have enough space in this little white spot, I'll do it in purple so that it doesn't, it's in a totally different color than what we had before. What I would do in this question, I don't want to use my quotient rule. You see you have a fraction? I don't want to use my quotient rule, so what I'm going to do is I'm going to move this x squared plus x to the top by using a negative exponent rule of a negative 4. And then I'm going to ask you if you can see that the x squared plus x is your inside function, inside the function that's to the negative 4. Yes? You see that the x squared plus x is inside that exponent of negative 4. So our chain rule says, do the derivative of the outside function, which is negative 4. That's a power rule. The negative 4 would come out in front, keep the inside the same, subtract 1 from my exponent, negative 5, multiply by the derivative of my inside function, which is 2x plus 1. That's as much work as you're going to show. And that's how you're going to do these most often. Recognize your outside function, recognize your inside function. Derivative of the outside, keeping the inside the same, multiply by the derivative of the inside. If we are using Leibniz notation, we substitute in a u for the inside function, which changes our actual question to y equals 3u to the negative 4. We find dy du. We find du dx. Because Leibniz's notation says the actual derivative dy dx is...
Excuse the interruption. Could all international students please now be dismissed and make their way to room 2E4? If we can have international students make their way to room 2E4. Thank you very much.
So then we can just plug things into our formula, substitute back, and you could play around with your exponent rules and change things, but you wouldn't need to. Leibniz notation kind of sucks. Isn't the purple seem like a lot less work? Okay? But you have to, like, you're going to get some crazy, like, I can put all the shortcuts together. I can have quotient rules with chain rules inside, with product rules inside, and you have to keep track of all of your shortcuts along the way. And some of the product rules get really, really long. When I was my second year of university, I was hired to teach the Calculus University Labs. And I don't know why this university, they had, at the front of the class, they had platforms as if the professor needs to stand higher to be more important than the students. So they had platforms at the front so the teacher or the professor was higher. So I'm teaching this lab, I'm on these platforms. There was 3 wooden platforms and a chair on there. And I was doing a product rule that was going super, super long. Because you know what, like, keep this the same, derivative of the second, keep the second the same, derivative of the first. And if they're big things, it can get really long. So I had a chalkboard, and it was literally getting so long that I had to put my knee on the chair to lean over and keep going. Which wouldn't have been so bad, except one of the legs of the chair was right in the crack between 2 of the platforms. So as I put my knee on it and leaned, the chair leg pushed the platform, slid through, and I did a volleyball dive in the middle of a calculus lesson. My textbook in one hand, splayed out on the floor. I think before that moment, nobody was paying attention in class whatsoever. And then all of a sudden, the lab assistant flies off the platform and falls on the floor. So they get quite complicated and quite long. So what are we going to do? We're going to do the purple method. We're going to say, first of all, we're going to write it in a way that it's just a chain rule, something inside of something else. Then what did we do when we did the purple? We did the derivative of the outside, which was just your power rule. We kept the inside the same. Notice this a lot in shortcuts, right? Quotient rule had it, power rule, product rule have it, where you keep something the same. The chain rule has that as well. You first do the derivative of the outside function, you keep the inside the same, then you multiply by the derivative of the inside function. And you can write it like that if you want, or I would keep it how it was originally. And we're going to do this from now on. But things can be complicated because you could have a cos inside of an e to the x. You can have a 5 to the x inside of a natural log, inside of a quotient rule. Things are going to get it's not complicated, but you have to have all of your shortcuts very clear in your head, and you have to know where you are in your shortcuts as you're going. So first of all, I would take this equation and change that 5th root to the 1/5 exponent. The power rule is really easy to see the inside function. The 3x squared plus 7x is my inside function. So derivative of the outside, the 1/5 comes out in front. I keep the inside the same. Subtract 1 from the exponent. Then I multiply by the derivative of the inside. So first I'm using my power rule for my outside function, and then when I multiply by the derivative of the inside, that's where my chain rule is coming into effect. And you could write this in a bunch of different ways. You can take that negative 4/5, move it to the bottom of your fraction. You could change that 4/5 back into a radical. So far, we've only had power rule once. So how do we recognize if something is inside of something else? So if I think of composition of functions like this, my outside function here was, here, my outside function, I'll label it as f of x. My outside function is just a 5th root. But what, highlighter-wise, what's inside of f of x is g of x. And g of x is the 3x squared plus 7x. Get that highlighter out again. Right? That is going inside for the x, because g of x is inside of f of x. So one of the things that I sort of look at is I sort of go, okay, if I have an outside function, which is the fifth root of x, where that yellow highlighter is where the inside function is going. So now let's see if we can see which is the outside function, which is the inside function. Some notations really lend well to that. Some are trickier to see. Okay? Here, would you say cos x is inside? Or would you say the 2x cubed minus 4 is inside? Okay? Probably I'd go with my gut on this one. Is 2x cubed minus 4. Feeling like that looks like the inside? You're absolutely right. Because it's like inside the cos. It like, when you look at it, it looks that way. So what do? We do the derivative of the outside first. What's the derivative of cos? Positive or negative sign? Negative sign. So we do negative sign, keep the inside the same. Multiply by, what's the derivative of the inside? The 6x squared. And of course, probably they would move this to the front if you simplified it, but it's perfectly fine to leave it unsimplified. One of the nice things about derivatives, if you're showing your work, you leave it completely unsimplified. If it's multiple choice, you're going to have to manipulate it. It's one of the ways they're like, you have to be good at your calculus rules, but then we're still expecting you to know all of your algebra rules from grades 9 to 12 pre-calc. So they'll check that you could you put this in front? Yes, I think this one's straightforward. This one doesn't have brackets. When you have brackets, it's kind of easy to see, well, what's in the brackets was the inside function, right? What two functions do we have? We have a tan x and we have an e to the x. Is the e to the x inside the tan x, or is the tan x inside the e to the x?
Tan and e.
The tan x is inside the e. How do we know it's inside the e? Well, if one of the functions is e to the x, do you see that that x has been replaced with something else? Whenever, like, your inside function is replacing the x on the outside function. Okay. So we start with the derivative of the outside, keeping the inside the same. What's the derivative of e to the x? E to the x. So this can cause all sorts of problems because you have one derivative which actually doesn't do anything. So the derivative of the outside is e to the x, but you keep the inside the same, so it actually keeps it the same. Then we multiply by the derivative of the inside function, which is the secant squared x. So in that exponential function, the inside function is where the exponent was. So I guess one way to sort of visualize it, here's our two functions that we see in this one. And we have to say, and we notice that this has got replaced with the tan x. So the tan x is the inside function because it's replacing something inside of e to the x. And the e to the x is the outside function as a result. So the biggest skill in your chain rule is making sure you recognize what's the inside function and what's the outside function. As soon as they're brackets though, it's almost all, like, what's inside the brackets is the inside function. So my outside function is ln of x, and my inside function is 5x to the half. What's the derivative of ln x? 1 over x. So we would have 1 over, keep the inside the same. See how you have 1 over, keep the inside the same? Multiplied by the derivative of the inside. Well, the 1/2 would come out in front. And you'd get x to the minus 1/2. And if I simplify this, I get 1 over 2x. All right. And I'm going to, this one is fun. I'm going to mess around with you a little bit. Have some fun. Okay? I'm now going to do, just, you don't have to write this down, you can just watch. I'm just going to get rid of the 5. Okay? You see how that's the exact same question? I just got rid of the 5. One over, keep the inside the same, multiplied by the derivative of the inside. So I would get, if I simplify this, what? The same thing? Why is it this, like, why is it the same? Like, check this one out. I'm not going to show a lot of work for this, but I want you to see if you can use your math skills to tell me, oh, I'm going to use 313. There's your derivative. Why does the 5 not matter? Why does the 313 not matter? Why does the 313 not matter? Well, if I used my log laws, do you remember your log law for multiplying? My log law for multiplying says I could add. Agreed? Natural log of 313 is a number. I don't know what it is in my head, because e to what exponent would be 313? I don't know. 2.7 to 6, 7? Feeling like, oh my goodness. Did I just do that? I just did that. I feel like it's somewhere between. Now I have to find out. Is it actually somewhere between 6 and 7? No, it's just before. It's between 5 and 6. Whew. That could have been disastrous. It's just a number. What's the derivative of just a number? What's the derivative of 5? 0. Derivative of 5.746 would be also just 0. So when I do the derivative of this, it's the same as the derivative of this. Now I used a chain rule, but I'm going to play around with this a little bit more. What other log law do you know? What can you do with an exponent? You can bring the exponent out in front of the log, right? So check this out now. When I do the derivative here, this will be 0. And this is just 1/2 times 1 over x. I get 1 over 2x that way too, and I didn't even have to use my chain rule. So sometimes you can use your rules, but also you can use other things you've learned in math to manipulate things. They may or may not make it easier to solve. As in this case, it kind of explains why the number in front does not matter. Logs are fun that way with using your log logs. Okay. Is this a chain rule? Yes. Because you have a negative x inside of 5 of x. Is this a product rule or a chain rule? Right? In order for it to be a product rule, if it was sine x natural log of x, then it'd be a product rule. But now the natural log of x is inside the sine. So again, one of the tricky things here is sometimes your brain might say, hey, you should do product rule. It's actually a chain rule, so we got to be careful what rule or what shortcut we have. So with 5 to the negative x, what's the derivative of 5 to the negative x? What's the derivative of 5? The outside function is 5 to the x. The derivative of 5 to the x is 5, keep the inside the same, natural log of 5. Then what's the derivative of our inside function? A minus 1. Do you see the chain rule? Derivative of the outside function with keeping the inside the same. Where's my inside? It's in this red box. I kept it the same. The derivative of 5 to the x is 5 to the x natural log of 5. If I kept the inside the same, I have 5 to the negative x natural log of 5. Multiplied by the derivative of the inside, which is just a minus 1. Second one, ln x is inside of sine. What's the derivative of sine? Positive or negative cos?
Positive.
Positive cos. So since we had a negative sine, we'd have a negative cos. Keep the inside the same. Multiply by the derivative of the inside. So when I was getting you to remember the shortcuts for the other ones, you can see how important it is, because now you have those shortcuts embedded in a new shortcut that you have to remember. If you forget the shortcuts, you can use the definition of the derivative and spend about 4 days on this question. That's perfectly fine. Can you even imagine plugging in the x plus h in here? Wow. Just off the top of my head, I can see at least 12 places you can get stuck. So the shortcuts are really handy, but we have to know them very, very well. What's the inside function? What's the outside function? The x cubed minus 4x is inside. It's inside a 1/3 to the x. So first we have to do the derivative of the outside, the 1/3 of the x, keeping the inside the same. What's the derivative of 1/3 of the x? 1/3 of the x, natural log of 1/3. So we would have 1/3 keep the inside the same, natural log of 1/3. Multiply by the derivative of the inside. There is someone can go on that corner. Okay. Not a product rule, because it's not tan x times sine x. Sine x is inside of tan x. So derivative of the outside, derivative of tan is secant squared. So we need to do secant squared and keep the inside the same. So if the derivative of tan x is secant squared x, the derivative of tan sine x would be secant squared sine x. And then because it's a chain rule, derivative of the inside, positive cos. anytime you have square roots, you'll change into fractions. Anytime your exponent's on the bottom, you'll often change it to an exponent on the top. Not necessary. You could also use the quotient rule here if you really wanted to, but you don't want to, because it just makes it longer. So you'll see that we often try to avoid if it's a 1 over, we just avoid the quotient rule. Or you could use the reciprocal rule, which you've already forgotten as a shortcut, because you'll never use it. Perfect. So we won't use that either. So now, do you see that the 9x cubed plus 5x is inside of an exponent of a half? How do you do an exponent of a half? That's a power rule. You bring the 1/2 in front, subtract 1 from the exponent, keep the inside the same. And then derivative of the inside. I find with my product rule, quotient rule, and chain rule, every time I do them, I say the words. Like, derivative of the outside function, keep the inside the same, multiply by the derivative of the inside function. I just want to, I don't want to blow your brains up by doing like a inside function that has a product. Can we end with one of those? There's so much fun. Well, yeah. Well, we have 2 more examples, and then I want to do one that's like a product rule inside a chain rule kind of thing. Okay. This notation is intriguing. Is the tan x inside the cubed, or is the cubed inside the tan x? What is the inside function? The tan x is the inside function. In fact, if you had written it this way, life would be so much easier, right? The mathematicians don't like those brackets. This is really easy to see the tan x is inside the cube. The way that it is here is a little bit harder to see. So how do we do outside functions cubed? We would put the 3 out in front, subtract 1 from the exponent. I even kept the brackets there. I don't mind if you do that. You could have just written 3 tan squared x. That's fine. But I find this easy to see at this moment. And then derivative of the inside function is secant squared. So you get 3 tan squared x secant squared x. And you know what AP might want to do on a multiple choice? AP on a multiple choice might have their multiple choice look like this. Can anybody see why this is the answer? What did I do? You get this in blue as your answer, and it doesn't show up in the answers A, B, C, or D. How would you get the answer of A? Any ideas?
Go backwards.
How would you go backwards? What did I do? How did I get that? You have an identity with secant squared. What's secant squared equal to? Tan squared x plus 1. And if I distribute, I'd get 3 tan to the 4x plus 3 tan squared x. Huh. That's where things that's what AP will do to try to determine who deserves 5s, who deserves 4s. Right? If you can't do the derivative, you're guessing on that whole question, and you're basically going for that 25% mark if you start guessing on everything. If you can do the derivative and it doesn't match up, then probably you have to go to your identities to fiddle around with it. Work backwards. Okay, I have to do two because I thought of a very, like, I'll hurt your brains a little bit on the first one, and then some of you might be concussed on the second. Just warning you. But on this first one, working backwards, did you get this? Okay. So we'll start off with just a little bit of a brain hurt for a challenge. Okay, I'm going to put together product rules and chain rules. So what I'm going to do here, I'm going to do an exponent of 3 there. And inside, I am going to do sine x times by 5 to the x. Do you see that the sine x times 5 to the x is inside the cubed? So if we were doing our wording for chain rule, we would say the derivative would be derivative of the outside function, keep the inside the same. No problem so far? Multiply by what? Multiplied by the derivative of the inside. Then when I go to do the derivative of the inside, do you see that it's a product rule? Okay? How do we do a product rule? We keep the first one the same, multiply by the derivative of the second one, plus keep the second one the same, multiplied by the derivative of the first one. That hurt your brain a little bit? Or was it, do you feel like if you say the rules out, it wasn't so bad? Okay? Derivative of the outside, keep the inside the same. But then when I had to do the derivative of the inside, I had to jump into my product rule steps to do the derivative of the inside. All right, now, yeah, let's go. Sorry, you saw the blink in my eye. Cosecant of okay. What's inside? The 5x cubed over ln x is inside cosecant. What is the derivative of cosecant normally? That's a shortcut I knew you'd forget.
Minus cosecant x, or cotangent.
Minus cosecant x cotangent x, right? The derivative, my outside function is cosecant, right? The derivative of cosecant x is minus cosecant x cotangent x. But we have to keep the inside the same. So what this will look like is minus minus cosecant, keep the inside the same. Cotangent, keep the inside the same. There's two insides in cosecant x when you do the derivative. So when you keep it the same, it gets kept the same twice. That's the first hurt your brain moment in this question. Then after we've done the derivative of the outside, we have to multiply by, switch colors, derivative of the inside. I'm going to run possibly out of room. It's a quotient rule. What do we keep the same in the quotient rule?
The bottom.
The bottom. So I keep that the same. Derivative of the top minus, keep the top the same. Derivative of the bottom over the bottom square. And this is our answer to this question. I wanted to show you a chain rule with cosecant because there's two x's in there. So it feels really wrong to keep it the same twice, but you keep it the same twice for both cosecant x and for secant x when you do those derivatives. Tomorrow, We are going to add chain rules inside of chain rules. And we are going to, what I want you to do for the last 3 minutes, I know there's not a lot of time. This is not homework to be handed in, but homework to have ready at the beginning of class tomorrow. We are going another mini review of derivatives. I feel like I didn't send enough. Oh, you only need.